Hello, welcome to Maths with EJD. In this video, we'll be talking about the Python code for mixed design ANOVA or split plots ANOVA. Having done one-way and two-way ANOVA manually, and especially seeing that two-way ANOVA can be quite computationally expensive or intensive, I just decided to not bother about the manual computation of the other ones because, as you progress, they become more complicated. For instance, imagine mixed design ANOVA, which otherwise known as split plot ANOVA, right? Which combines between subjects and within subject factors to examine multiple variables simultaneously. In the context of ecology, that would be something like interspecific, that is species, one species to another species interaction, and intraspecific, that is species, individuals of the same species competing with themselves. So that's the kind of idea here. Like between subject is like interspecific, while within subject will be intra-specific. So that's the kind of thing. So you can already imagine that the math is going to be really intensive. An example would be like studying the effect of a medication across different time points, that is within subjects, and across different groups between subjects. Now, across different time points would be like, okay, say you have 10 people, and then you want to see the effect of medication on them, like maybe 10 people, different time points, you take their measurement, whatever you are measuring to see the effect of the medication at maybe two or three different time points. Then you now combine that again with administering the same medication on another group at different time points. So it's like you're looking at what is happening between them, within the group, and between this group and the other group. So it's more like um you're combining the normal, like say you're combining a two-way ANOVA with repeated measures. That's the kind of idea you get from here. In the case of two-way ANOVA, you're talking about independent groups. But when you come to repeated measures, right, you're talking about groups that have something in common, right? So that's the kind of thing that is happening here. So that's why it's called mixed design ANOVA or split plot ANOVA. And the hypotheses are three. You know, the first null hypothesis will be the group differences between subject factors have no effect on the patient's response to the medication. So, the difference between this group and that group has no impact on the patient response. Then the second null hypothesis would be that the timing of measurements within subject factors has no effect on the patient response to the medication. For instance, so if a measurement is taken in the morning, another one is taken in the afternoon, another one is taken in the night, or maybe one is taken this month, the other is taken the next month, and another is taken the month after, that timing has no effect on the patient's response to the medication. That's the second null hypothesis. And the third null hypothesis is that there is no interaction effect between the group differences and the timing of measurements on the patient's response to the medication. So it's like, so if you talk about timing within the group and differences within this group and that one, that has no effect on their response to the medication that is being administered. That's the kind of thing going on there. So the alternative hypothesis just be to counter those first three. That the first one will be the group differences have an effect on the patient response to the medication. So the fact that this group is different from that group, it has an impact, right? Maybe this group of people respond differently to the medication than the other people. Then the second one is the timing of measurements has an effect on the measurements on the patient response to the medication. So if you take the measurement in the morning, afternoon, or evening, there will be significant difference. And the third alternative hypothesis is that there's an interaction effect between the group differences and the timing measurements on the patient's response to the medication. So you see, there's that combined effect, that the fact that you're taking the measurement at different time points and then you're measuring different groups, it has an impact on the final result. So that's what the alternative hypothesis will be. So let's see the code and see how that looks like. So of course, we are using pandas for data analysis. We are using stats model. That's probably where we are going to get yeah, for instance, okay, yeah, I think it's always good to put line numbers for easy referencing. Let me see where the actual fit is done. I think that is of course we have a definition, if a function defined from line 30 to 34. So that's around where the whole fitting, yeah, where you see fit, that's line 32. That's where that is being done. So Then the see how the data looks like. We have group A and we have group B. So in group A, at time one, whatever the time is, we take the measurement of the effect of the medication, time two, time three, the same for group B. So you have two different groups and then you have different time points. So if you just take group A responsibility with the different time points, that is like repeated measures. So it's like you have repeated measures for group A, repeated measures for group B, then you're not combining them together. So giving the vibe of like repeated measures plus the normal one-way ANOVA or something like that, or two-way ANOVA, as the case may be. Then in line 20, I mean, in line 21 to 26, for instance, or in fact to 28. So there, the data is converted into a data frame with all of those things. So list range 1 to 11 is more like you have in Python, if you say 1 to 11 in a range, you're actually talking about 1 to 10. It's like you have 1 to 10 times 6, making 60, because you have 30 data points for the first group, 30 data points for the second group, based on the different timing, making 60 altogether. So you have 10 subjects repeated for 3 points for both groups, so making 60. So that's like 10 times 3 times 2. And then you have you have the time one, 10, time two, 10, time three, 10, and so on and so forth. And then you have the group A 30, group B 30. That's the 30 observations for each group. And for the response, you have group A response plus group B responses. That's combining responses for both groups. And then you're returning the data. So then we can have, of course, if we want to visualize the data, if you so wish. And to do that, all I just need to do is to say print data. I just want to see the whole data. Okay. Then after that, I can actually put a blank print to give some space in case something else is printed afterwards. Then in line 35 to 39, that's where the actual fitting is being done. So, you see the setup. So you define fit ANOVA data, and the model is ordinary least square. Talking about response to C groups, to C time, to subject, all of that. And with the data that is declared here, and then you're fitting that. And then ANOVA results, you can have that here, SM, the stats, ANOVA, blah, blah. And then you return the ANOVA results. So from 41 to 46 is where you're making the decision whether to reject or accept the hypothesis or so. So decide whether to reject the null hypothesis based on p-value. So if p-value is less than alpha, then reject the null hypothesis for hypothesis, and then fail to reject the null hypothesis for hypothesis. Hypothesis was first mentioned here, so this is being referred to now. Okay, then you now define a main function now where you talk about the data is created. You can preview the data. Okay, in fact, you can see what the data looks like. Of course, this is going to give you everything. So it means I don't even need the data here like I did previously. So it's not needed because the job is done down there. So, and then, so we preview the data. Step 3 now, we create data, display data preview, then we fit ANOVA model and display data results. So ANOVA results now fit underscore ANOTA data. Then we now have Mixed-Design ANOVA results. So it will give us all the necessary results. Then step 4 is extracting p-values for decisions. So p-value of the group, you extract using that what you have in line 59. P-value for time, you extract from line 60. P-value for interaction between timing and grouping, you do that too. That's why you have C group, C time in line 61. And then from 64 to 70, you are displaying decisions based on p-values to say whether you're agreeing to accept the null hypothesis. That's hypothesis with ES, that is, because you have 3 null hypothesis and 3 alternative hypothesis. So after all the story, if you run this now, you see the kind of thing you get in one blow. So you see the data displayed this way. You have 60 data points. Never mind. I mean, Python starts counting from 0. So you have 0 to 59. But of course, for the data itself, it's like you have group A, three different time points. So you have for each time point you have 1 to 10, time 2 1 to 10, time 3 1 to 10. So for group A you have 1 to 10 in 3 places. For group B you have 1 to 10 in 3 places also, with the corresponding values of the response, the medication response. Then you now have the mixed design ANOVA results. So for the C group, you have the sum of squares. You have for C time, you have the sum of squares. You have the degrees of freedom right there. Then you have the F statistics, as you can see right there. And then you have the probability that those things are greater than F. So at the end of the day, you reject the null hypothesis for the group differences. Okay, I mean, why is that happening? I guess it may be necessary to visualize the p-values. Can we pull that off? I believe we can. So you can just print. So let me print in one blow. Uh, the p-values, the p-values are this. Can we do all that together? Or let me do it in one by one. The p-value. Okay, at least let me see one of the p-values. The p-value for group or groups is this. So I just copy this p-value group just to see what the value looks like compared to the um, critical value. So we can do the same for the other p-values. This now, we have p-value for time, or should I say times? So that's p-value time, p-value time. Then lastly, we have p-value interaction, p-value for interaction. So that is p underscore value underscore interaction. Okay. Well, I want to have a blank print to make it stand out. Okay. And then maybe another blank print after this to make it stand out still. So if I do this now, okay, we have the p-values here. So you have 2.7. I mean, 10 raised to minus 48. That's very small, very close to zero. So for group and time, very close to zero. So they are obviously going to be less than the critical value 0.05. And this one is greater, you know. So you see, you reject the null hypothesis for the group differences, reject the null hypothesis for the time measurements because these values are small. But then you accept the null hypothesis for the interaction effect between groups because the p-value is bigger than 0.05. So that's how that goes. So if you reject the null hypothesis for the group differences, right, that means there's no significant difference based on grouping, and reject the null hypothesis for the timing of measurements. That means there is no significant differences based on timing, and then fail to reject the null hypothesis for the interaction effect between two group differences and timing. So it means that there is significant difference observed based on the interaction of grouping and timing. That's what that simply means. And that's how that goes. If you have not subscribed to this channel, be sure to do that. Hit the notification bell also so you can always get alerted each time a new video is released. Don't forget to comment. Tell me if you want me to teach a topic or solve a problem. And also like, then share so that more people can have access to this great learning. Have a nice time. Bye.